So, hello everybody. Good morning. It's a place for me to introduce our first speaker of this morning. She's the Dr. Hanna Furmańczyk from the Dance University. And as always, I don't repeat the CV. You can check in our page. So let me tell you about my relation with Hanna. Hanna is I met Hanna maybe 10 or 12 years ago in dance when I visited the Polytechnic of Dance. And in this time, Hanna has some academic administration position in Dance University. So she was very important and occupied person. But it was very nice for me that in every time that I visit dance, she has time to drink with me a coffee, sometimes a wine, ask me how is Mexico, how is your family, etc. It was very nice. And then I start to think to work with Hanna because moreover I heard some of his conference and I think she works in very nice topic. But really, I was afraid to work with Hanna because she looks very strong woman and person, very fast. I say, oh no, Hanna will kill me after 2 days because I am very slow, etc. But it was very funny because with the time I discovered that Hanna was afraid of me too. So maybe for equivalent reasons. But okay, someday we decide to start. Hanna visit me in Mexico for 3 times. And I think that both of us discover this other part that has not to be with our mathematician face. We discover the woman, the friend. So independent of our mathematician work together, I am really very happy to introduce to Hanna, and I am very happy that we quit this afraid between us, and we can work, talk, and we still continue drinking coffee and wine every time that I visit dance. So thank you very much, Hanna. You can start.
Yes, thank you, Rita, very much for the very nice introduction, and thank you all the organizers to invite me and to let me know, to give me such opportunity to give here in this very nice conference a talk. The subject of my talk, first of all, do you see my slides? Yeah, I don't.
Yes.
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 Super.
Yes.
Okay, super. If something is too fast, or if something is hard to understand, please interrupt me in any moment of my talk. Don't hesitate to do this. I would like to I would like to show you some applications, some real problems, and I would like to show you how you can model the problem, real problem, in the language of graph theory or the language of combinatorial optimization and try to solve the real problem. Maybe not always solve as good as we would like to solve, but nevertheless, we can really help in solving real problems. And let's start from the very beginning. Let's come back to the 18th century, to Königsberg, to the problem that I believe that most of you knows very well. It's the problem connected with doing walk in Königsberg. As we know, Königsberg is located on the banks of Pregola River. We have 2 banks of the river. We have island, one and peninsula, and people start to put the question whether there is possible to start walk in any place of Königsberg and cross the bridge, every bridge. Then they had 7 bridges. So they wanted to have such a walk that during that walk, we wanted to cross every bridge exactly once. And this is the problem definition. And maybe there was important that I need to add that we start in one point, we do a walk, we take a walk and return, to the starting point. Maybe not all of you knows that this question was formulated by Professor Kuhn, mathematical teacher, math teacher in Gdańsk, in Danzig Academic Gymnasium. It was very good gymnasium. And he put such a question and sent this question to Euler. Euler then was very known mathematician, and Kuhn wanted to discuss this problem to him. Euler noted that the walk actually doesn't depend on choosing the point of the landmass. It is not so important. It doesn't matter when we start in which point of the landmass, but it's only important that how we order bridges in our walk. So he modeled that problem he simplified the problem, and then finally he modeled the problem with a graph where vertices correspond to landmass and edges correspond to the bridges. And the question that Professor Kuhn puts is equivalent to ask if there is a path that starts and ends at the same vertex and traverses each edge exactly once. Now we call such a path, such a cycle, as Eulerian circuit or Eulerian cycle if a graph has such a cycle. We call such a graph Eulerian graph. And we probably all know that it's very easy to verify whether the graph is Eulerian or not. First of all, we need to check that the graph is connected, and then every vertex needs to have even degree. If we have a graph with exactly 2 vertices of odd degree, instead of cycle traversing all edges exactly once, we can have a path traversing each edge exactly once. So if we come back to the graph that is a model for Königsberg problem, we see that the answer in this graph is negative. We have 4 vertices. These vertices of degree 3, the same here, and we have here 5 incident edges to this vertex. So this graph certainly is not Eulerian. But nevertheless, the conditions, the properties can be easily verified, and it can be verified in polynomial time. And moreover, we have polynomial time algorithms that returns Eulerian cycle, Eulerian circuit, if only the graph has such a cycle. Probably the most known algorithm is Flory's algorithm that can be formulated as one sentence: don't burn your bridges behind you. And probably most of you knows the problem, knows the algorithm. We choose any vertex as a starting point, and then if only we have, if only we have one edge incident to the vertex S, we traverse that edge to the next vertex and remove that edge along with vertex X. Otherwise, if there is only one edge, we have no choice. So we need to choose the edge. We remove the edge, we remove the vertex and go further. And here we've got an example. Let's say we start from vertex A. Here we have two incident edges to vertex A. We can choose any of them. No one is a bridge. A bridge is in a graph is an edge that after removing this edge, connected graph stops to be connected. We can, in results, we have disconnected graph. So these two edges are not bridges, so we can choose any of them. Let's say I choose the edge from A to B. We traverse this along this edge and we delete. In B, we have three further edges incident to vertex B. Again, no one is a bridge, so we can choose any of these four. I will choose edge from B to C. We, of course, delete this edge. From C, it's the same situation. I can choose any of these three. I will choose that one from C to E. And now we have an edge from E to H. That is a bridge. After removing, if we remove this vertex, the graph would be not disconnected after this. And we wouldn't come back to traverse the edges in this part. So we cannot choose this vertex, this edge, sorry. So for example, from E, we go to D. Now we have one edge incident to D, so we need to choose vertex C, the edge to vertex C. We remove this edge. It was the last edge incident to vertex D, so we need to remember about removing vertex D. Now from C is the same situation. It's the only one edge, so we removed. From F to E is also only one possibility. And now we have to choose edge from E to H. We need to remember about removing the vertices if they are isolated after the deletion of an edge. From H, from vertex H, now we cannot choose this edge from H to A because it's a bridge. Again, this edge is forbidden, so let's say we go to B, from B to G, and from G to H, B, G, H, and finally to A. And we have Eulerian cycle. This algorithm is very known, but its efficiency, it's not so good as we could expect, because of course it's not to avoid to traverse all edges. So the algorithm is linear in according to the number of edges, but every time we need to check whether the edge we want to choose, it's a bridge or not. And this part increased the computational complexity of the Floris algorithm very much. So actually we have polynomial time algorithm, but we may say fight for more efficiency, for more efficient algorithm. And we have another algorithm called Kirk-Kolzer's algorithm. This algorithm starts actually in the same way. We start from the any vertex X, and we follow edges. We follow a trail of edges starting from X and returning to X. We are not obliged to use all the edges because then we will finish with the Eulerian cycle. We are interested in any trail starting in X and returning to the same vertex. And after this step, we will extend the trail into the bigger one, and finally we extend the trail into all edges, and we finish with Eulerian cycle. So as long as there exists a vertex that belongs to the current tour, but it has adjacent edges outside the tour, we start another trail from vertex U, following unused edges until returning to U. And we join the two tours into one bigger. And here the complexity is much more efficient, it's better for us. And let's look at the same example, how we can proceed with this problem here. Of course, we can start from A. We can start from A, and let's say I will choose such a trail, starting at A and finishing in A. So in the first iteration of the algorithm, I have such a trail. Okay, but of course, there are other edges incident to these vertices that I have chosen, A, B, G, H, outside this trail. Of course, A and G not, because all edges incident to these vertices are here in the trail, but we have edges incident to B and we have edges incident to H. So let's say that we will start in B. For example, we will choose such a trail. This trail is B, C, E, H, B. Yes, B, C, E, H, B. And instead of B here, in the previous trail, we put the second trail. So together, after the second iteration, we have such a big trail. We go from A to B, then we go to C, to E, to H, to B, to J, H, and A. And again, we see here in this part of the graph, we have all vertices and edges, but in this part, there are some edges incident to C and E. They are outside our current trail. So we can choose actually starting from C, then go to D, E, F, and C. So now we should join the previous trail with the new one. Sorry, not B by D. C, D, E, F, C. And instead of this C, we put here what we joined. And finally, we have Eulerian cycle A, B, C, D, E, F, C. And further part from here, E, H, B, G, H, and A. This algorithm is more efficient, and we should think about using exactly this algorithm or even better. Nevertheless, Eulerian cycle is very useful in many problems. For example, we can apply these algorithms to solve some puzzles with drawing without taking off the pencil from the paper. We can use finding Eulerian cycles in Chinese postman problem, also in the rural version. we have a lot of such applications that in some sense, in some subcases, finding Eulerian cycles can really help us. But nevertheless, we have a problem that can be solved by mathematical tool in polynomial time. Efficient, more efficient, less efficient, but nevertheless, there is a polynomial time. So we are really very happy. We may say that our dreams come true in such situations, and sometimes it happens in life, also in combinatorial optimization. But such situations, of course, very comfortable for us. But unfortunately, life is brutal. Some real problems, it's really hard. And the question is, what if a problem is really hard? By hard, I mean in the context of computational complexity. So we may say, never stop dreaming and working hard towards achieving your dreams. It's a sentence that I hope all of us follow in our life, but also in the scientific life. When we meet hard problems, we should remember that we can still work hard and do some improvement even in real hard problems. Because always we can, for example, if we cannot solve the problem to optimality, we can always give some heuristics, we can always give some algorithm, maybe approximate algorithms, quite good algorithms that return the solution, maybe not optimal, but nevertheless quite good, that make us still happy. And now I would like to show you some real problems and applications. To solve this problem, we will apply some models of graph coloring. All of models that I choose here, the first one is it's classical graph coloring. In all the cases, I focus only on vertex coloring. We know that we can color edges, both the elements simultaneously. There are many other problems, models of graph coloring. All of them are hard from the point of computational complexity. Finding optimal solutions, or even finding if the graph admitting coloring with some specific conditions with k-colors, it's also hard. But nevertheless, we work on these problems and we want to give sometimes partial solutions, sometimes approximate solutions, but nevertheless, we still believe that our work makes sense. Okay, let's start from the proper coloring. The proper coloring is an assignment of colors to the vertices of a graph so that no two adjacent vertices are assigned the same color. We avoid monochromatic edges, and we have such an example, a graph. Okay, we have a graph, and we try to color this graph using optimal number of colors. So we are interested in using as small number of colors as we only can. So here we see that we have 4 vertices inducing complete graph. So it means that every vertex is adjacent to any 3 vertices from this 4. So we need to use 4 different colors for this part of the graph. And we know that we cannot use smaller number of colors. And it's quite easy to extend the coloring into entire graph, because here we've got vertex A uncolored, is adjacent to 1, is adjacent to 2. So it may receive color 3. The same here is color 2, color 3, so we can put 1. 3 and 4 for E, it's forbidden, but for example, 1 is allowed, and here, for example, 2 is allowed. And we have proper coloring of vertices of this graph. The smallest number is called chromatic number of the graph. In this way, in this example, we need to use 4 colors. And we cannot use less, so this 4 coloring is optimal. We can look into this, into coloring as to partition vertex set into subset. And in our example, we divided our vertices into such subsets. First one, V1, there will be formed by vertices colored with 1. So we have vertex H, vertex C, vertex E. V2, there are vertices, of course, independent. Every such set needs to form independent set. So we have V2, the vertex is colored with 2, so it's vertex B and vertex G. V3, we have 2 vertices colored with 3, and finally 1 vertex colored with 4. So our vertex set was divided. We have a partition of the vertex set into 4 independent sets. We call them as color classes. So we may look as a coloring, problem of coloring is a problem for partition vertex set into classes. Yes, here we have such a coloring. I already mentioned about color classes and chromatic number. And now let's imagine such a situation. We have 10 groups of people, 10 committees, A, B, C, up to J. Yes, we have 10 groups of people. For example, committee A consists of guy 1, 2, 3, and 4. But we can look at the other committees, and for example, the guy 1 is included not only in committee A, but also is included in committee B only. But in another committees, for example, here we've got 15, and here is also 15. So some committees contain the same people. And our goal is to schedule the meetings of these 10 committees. So here we can model the graph, model the problem with a graph where vertices will correspond to committees, and there will be H joining 2 vertices if the corresponding committees overlaps membership. Let's look at this example. Again, the same committees. Committee A is here given by a vertex, and we have vertices, 10 vertices, A, B, C, up to J. And for example, there is something in common between A and B committees, so there is an edge between the vertices. For example, committee G includes guys from 10, 11, 12, 13, 15, 16, and J only 18 and 19, so they don't have nobody in common, so they are not joined by an edge here in the graph. Yes, everything is clear up to now? Okay, I don't hear any remarks, so we can continue. The question to the problem is how many hours are needed to give possibility for all the committees to meet and to do something good. So we can color this graph and solve this problem by coloring the vertices of the graph. For example, here we've got vertex D. I will assign color 1 to this vertex. Of course, none of its neighbors cannot receive color 1, so we use color 2 here. Cannot be 1, neither 2, so we assign color 3. Here we can put 2, 3, 2, 3. What's further? Here we have 2, 3. Here can be 1. Here for vertex H, it is adjacent to a vertex colored with 2 and a vertex colored with 3, so, and a vertex colored with 1. So unfortunately, we need to introduce new color. And for J, 1 is forbidden, but 2 is allowed. And we have coloring with 4 colors. It means actually that we need 4 time slots. We can assume that every meeting of committee will last 1 hour. So we can first time slot, second time slot, third and fourth. In the first time slot, we can have a meeting of committee D, committee E, and that's all. So the cardinality of the color class for color 1 is 2. We have 2 vertices colored with 1. Now we have to the second time slot, we schedule the meeting of committee A, committee F, committee E, and committee J. So the cardinality of this color class is 4. Third time slot, vertices B, C, and G. And the fourth time slot is only H. So we have cardinality equal to 1. And we know that in fourth time slots, we are able to organize all the meetings for all 10 committees. So proper coloring will help us in solving this problem. But there is another problem. We have such a company, such a building that we only have 3 classrooms. So unfortunately, we cannot plan for meetings in one time slots because we don't have space to organize such 4 meetings simultaneously. So we need another model of graph coloring. First thought, it's okay, there is a bounded coloring where we have a bound, a constant number that it's a bound for the cardinality of each color of color classes. Here there should be 3 bounded coloring. Of course, it may be applied, but here we can also apply another model of coloring, equitable coloring, because if we would balance the coloring, if we change the frequency of usage of each color to more balance, then the usage of classrooms will be more effective. And what we can do here, we can recolor one of vertices now colored with 2 into the less frequently color is 4. So let's try to recolor one vertex from 2 to 4. Of course, we cannot do it with vertex E because this vertex is adjacent to the vertex colored with 4, the same with J, but we have vertex F, here can be 4, and A also can be 4. So I will recolor this vertex. What happened? We have in this second color class only 3 vertices. And in the fourth color class, we have 2 vertices. And now our restrictions that we have only 3 classrooms, it's nothing bad for us, because now we have such a coloring, then in every time slot, we have 2 or 3 meetings. So 2 classrooms are occupied or 3 classrooms are occupied, and this is okay. And this is, with such balance frequency of usage, the colors, it's called equitable coloring. We say that equitable coloring is of a graph is a proper vertex coloring, yes, but with additional condition. The sizes of any 2 color classes differ by at most 1. So we want to use every color. The best way it's the same number of time, but if it's not possible, we allow for the difference 1. And here is the coloring equitable. The usage of classrooms is most efficient in this type of coloring. Unfortunately, as I mentioned, as well as proper coloring, the same with equitable coloring, the problems in decision version, or here we have decision vertex for proper coloring. So we have given graph and we have given number of colors, and we ask whether there exists a proper K coloring. So coloring with K colors. And we know that if only K is 3 or more, then such a coloring is NP complete. The answering to this question, whether it is possible or not, so or yes or not, is hard to achieve in polynomial time, if only we can say some hypothesis about classes of problems is holds. Hypothesis holds. Okay, here we've got equitable coloring. I mentioned about it. Okay. What is the relation between complexity of proper coloring and equitable coloring? At first glance, we are thinking, okay, equitable coloring is a proper coloring with additional constraints, so it cannot be easier. Can be the same stutter or even worse. So we know graph classes, for example, bipartite graphs, corona of cubic graphs. We show that the problem of equitable coloring is really harder than proper coloring. So for proper coloring, these classes can be colored polynomially, but equitable coloring, no. But there is a case when equitable coloring, surprisingly, appears as an easier one. We are talking now about optimization version, not decision version. So we are interested in coloring, equitable or proper coloring with optimal number of colors, the smallest number of colors. So let's imagine that we take any graph, completely any graph G, and we add one vertex V that it is adjacent to any other vertex of graph G. And we want to color this graph equitably in the smallest number of colors as it's possible. Okay, so we can assign color 1 to the vertex V, because every other vertex is adjacent to that colored with 1, so color 1 cannot be used anymore. The coloring must be equitable, so it means that any other color can be used only at most twice, once or twice. So actually, we need to find independent pairs of vertices not joined by an edge, that can be assigned the same color. only pair. Next pair, maybe here there are some edges between that. There is important that there is the two vertices cannot be linked by an edge. And we assign next color and so on. So actually, such a problem can be easily solved because it is enough to take a complement of a graph and the vertices that we want to assign the same color in graph G, here in the complement of the graph, they will be linked by an edge. So actually, we want to find matching the set of independent edges in the complement of graph. Maybe some vertices will be isolated and we can use only each color only once, but some of them none. And we can solve the problem of optimal equitable coloring in polynomial time, because we are in polynomial time are able to find such a matching. For proper coloring, no, because of course, color 1 will not be used here in graph G anymore, but color 2, 3, and so on, they can be used anytime as we want. And this problem is still hard. It's still hard for proper coloring. So surprisingly, we have also examples with the opposite dependency between the two models of graph coloring. Okay, but what we can do more? We can look at particular graph classes. And in one moment, a few years ago, we were interested in chordal graphs. Chordal graphs, there are such graphs that when they have cycle of length 4 or bigger, longer, such a cycle, induced cycle, needs to have some chords. In other words, we don't have in chordal graph induced as an induced subgraph a cycle C4, C5, and so on. Always, if such a cycle exists, they need to have inside chords. We're interested in this class of graphs, and we first look at the dependencies between the class of chordal graphs and others. Here, maybe it's not important. Everything is here maybe not important. There are important chordal graphs, and for us, we know that the subclass of chordal graphs are interval graphs. Interval graphs are such graphs that in every vertex we can assign interval on the line in such a way that two vertices are adjacent. So it means they are linked with an edge, if and only if the corresponding intervals intersect non-empty. Yeah, so we have such a equivalence between vertices and intervals on the line. For example, here we have interval corresponding to vertex B and interval corresponding to vertex. Something happens? No. And B and D are not adjacent, not linked by an edge, so the intervals are disjoint. And we found the information that for interval graphs, equitable coloring is still hard. So at once we had a corollary that for bigger subclass of graphs, including these hard cases, the problem of equitable coloring cannot be easier. There also will be hard. So we start to look for another subclass of chordal graphs in which we believe that we can do something interesting. And we have chosen block graphs. Block graphs are such a graphs also called clique tree, in such a graphs, every block, it means maximal two connected component is a clique. And here we've got an example. And we've got, for example, we've got here a block, it's K4, so it's a clique. Here we have got a block, it's K2, 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 here is K4, and so on. We may look at this as a tree, but instead of vertices, we have cliques. But unfortunately, it turns out from different other papers, maybe it's not important what it's written here, but it's the most important, it's that the problem of equitable coloring is not polynomially solvable in block graphs. Of course, under the assumptions about the hypothesis that P is not equal to NP, and we have other hypotheses as well. So again, we weren't lucky. Also in this subclass of graphs, but we really believe that we can do something interesting for block graphs. And we formulated conjecture for the smallest number of colors for equitable coloring. This means for equitable chromatic number. Maybe it's not important what is on the left and on the right. You don't need to understand what is it, but what is important? Important is that we need to notice that we have here something, and on the right side, we have the same plus one. So actually, we claim that the number of colors admitting optimal equitable coloring of block graph has two possibilities, one or plus one. Yes, this one or this one. So it's a similar statement as in the Wissing theorem, where we also have only two possibilities for values of chromatic index then, but deciding which one is appropriate, it's difficult to do. Yes, so nevertheless, if we prove this conjecture, we have proven this conjecture for many block graphs, but still there is a group of graphs that we are not sure whether there is a true or not. So we are able to give one absolute approximate algorithm. So at worst case, we'll use at most one color more than it's in optimal case. Okay, if somebody is interested in details about equitable coloring of block graphs, here we have some reference. This next model of coloring, the last one, I guess, there is a bichromatic number. It's quite different from the previous two models, because here we are interested in the largest number of colors admitting coloring, K coloring, but not this coloring also have some additional demandings, and we want to color a graph with K colors. Yes, we need to have proper K coloring. So we want to partition vertex set into K color classes. Each color class is an independent set, but in each color class, we want to have B vertex. This means it's a vertex that is adjacent to at least one vertex in every other color class. And in each color class, we also have such a B vertex. Of course, we need to have enough number of vertices of high enough degree, the candidates to be B vertices. And here we have an example, but maybe it's more interesting how, when, where we can apply this B-coloring. Let's imagine such a situation. We work for the company X, and our boss told us to organize an integration event. We know that people who work with the same department know each other very well, but between departments, it may demand some integration. Okay, so we want to divide people into groups. In each group, it is desirable that people doesn't know each other. So we want to, they will form in the graph independent set, but we want to ensure good communication between groups. So in each group of people, we want to have such a group that this person in each group has friends, let's say friends, knows the people from other groups. In each group, they know at least one such person. So actually, we want to color a graph. There will be a model of this problem in B way, because the people who will ensure the communication, there will be B vertices in our B coloring. Because we want to, we don't want to have the groups to be too large. So we want to divide people into the maximum number of groups. So actually it's optimal B coloring. So there are also some nice results about B coloring. The big focus is put to regular graphs, because in regular graphs we have every vertex has the same degree. So every one of them is a good candidate to be B vertex. So people think about regular graphs. We have some conjecture, very nice conjecture. Here I put some information about this conjecture, but I'm start to be short of time, so I need to omit some of my slides. We also, me and Magda Detra, she is probably here, and other people from our group, we do some contribution to this topic to show that some conjecture according B coloring of regular graphs is true. So we do some contribution. Again, if you are interested in details of this model of graph coloring, I refer you to some very nice survey about bichromatic number and related topics, written by Istok, Peterind, and Jakovac. There are a lot of models of graph coloring, and actually each one of them can be applied in some real situation. I put here packing coloring. Rita also worked on this model. This model is connected, introducing of this model was motivated by broadcasting frequencies to radio stations. When we have stronger signals, weaker, and the distance between vertices, between the places that may receive the same frequency is important. And in this model of graph coloring, we look how far the vertices are from each other, and then we assign appropriate color that represents the frequency. So if you are interested, there is also a very nice model. As I mentioned, we have a lot of models of graph coloring and a lot of their applications. You may find a lot of books about coloring of graphs. I would like to recommend that one, because this one is edited by Professor Marek Kubala. We will talk about him tomorrow. on the closure session. So I would like, I wanted to put this, his book here. And I hope I encourage you to think about coloring and about graph theory or even wider combinatorial optimization. And thank you very much for your attention.
Thank you very much, Hanna. Very, very nice talk. Everything is nice, and in the spirit of this conference. So really, thank you very, very much. So I don't know if we have any question to the people here or on Facebook. Okay, Professor Martin.
Hi there. Thank you very much for that nice lecture. I seem to miss where equitable coloring is efficient. There was one part in when you were first introduced the topic of equitable coloring, where you said that it was seemed to be tractable. What was that special case?
Here I mentioned the equitable coloring because we want to, when you balance usage of the colors, then, for example, if you have meetings, schedule meetings to time slots, and if you don't have meetings, for example, in one time slot, a lot of meetings, and in another only one,
Yeah.
so this is the efficiency. Yes, for me, this is efficiency of this equitable coloring. For example, when we want to organize the plan for students, timetabling, it's also very important that it's not 10 hours in Monday and 2 hours on Tuesday, yes, but we want to balance the usage of the colors. So in such a cases, equitable coloring is very useful.
Yeah, I agree 100%. It's very useful. I just wondered, since you said that equitable coloring was hard for interval graphs and even block graphs, is there any, maybe it's just a trivial class where equitable coloring is actually polynomial?
Yeah, there are a few such classes. Of course, cycles, paths, trees.
Trees.
But okay, but not forest. But not
Oh,
forest.
no. Okay.
Yeah.
So
because it's the case of bipartite graphs actually here.
Yeah.
Because in proper coloring, you need to have only two colors for forest, for disconnected bipartite graphs. But if you want to spread colors equitably, you need to try to solve the partition problem actually.
Okay.
What
So
is hard.
even for trees, it's hard?
For forest, for trees,
Yeah.
I don't think so. I don't remember. I don't want you to lie here, but for forest, definitely it's hard.
Okay. Thank you.
Thank you.
Any more questions, comments? No questions on YouTube by the moment. Okay, if nobody, if there are not questions or comments, I say thank you again, Hanna. Very nice.
Thank you
for your talk. Thank you very much, and we will continue. In I think we can take 2-3 minutes before to start with the next talk of this morning, this evening, for many of us.